There are still some people who need to take the quiz, so like AAC, other things. So don't talk about it on Discord, please. I know it's hard. I know you want to, and I would love for you to all just discuss it right now, but can't. So hold on to those thoughts. I don't know yet. Obviously not a full exam, but part of an exam, less than 50, maybe 20 exam points. So solid, but not crazy. All right, so Gibbs free energy. What is Gibbs free energy? What does it represent? Yeah, chemical potential energy, essentially. We can think of it that, at least in an analogy with mechanical potential energy, that things want to decrease their potential energy. And so we can actually see that as a function of even K, which we'll discuss more how G is related to K later. But if we can calculate G using delta H, which is the enthalpy or the heat from the system, and delta S, which is the change in the entropy, and remember the heat portion of this is really how much changing our system adds or removes heat from the surroundings, which increases the entropy of the surroundings. So there's like a balance between the two. For a reaction that changes, whether or not it's spontaneous with temperature, we get our reaction that, or I guess according to Q, K, something that looks like this, where the reaction will sort of fall, if we draw it on a graph this way, in potential energy towards some minimum potential energy. And in this case, that happens to be where Q is equal to K. But before we really get to that, we got to talk first more about, actually, talk about how these are related first, because there's really only 4 cases. We have delta H and we have delta S. And for some of those combinations, reactions will always be spontaneous. For some of those combinations, reactions will always be non-spontaneous. And then the other 2 cases are where it's spontaneous at high temperatures or spontaneous at low temperatures. And that depends on the signs of delta S and delta H. I think this is this is an exothermic reaction. So for an exothermic reaction, if delta H is negative, and delta S is positive, and we can know that delta S is positive, at least for this reaction that's a gas, bless you, because I go from 2 moles of gas to 3 moles of gas. Increasing the moles of gas increases the entropy, so there's a positive entropy. So if delta H is negative and delta S is positive, then for any temperature, it's still going to be positive. Or sorry, it's still going to be negative. Delta G will always be negative. And again, thinking about the bigger picture, if I'm adding heat to the surroundings by doing this reaction, that increases the entropy of the surroundings. And we want entropy to, or at least the universe wants entropy to always increase. So delta H means that we're releasing heat into the surroundings, which means that the entropy of the surroundings is increasing. And then because my system itself, my reaction itself, is going from fewer gas molecules to more gas molecules, its entropy is also increasing. So if the entropy of everything's increasing, then there's no situation where that's not going to be non-spontaneous. But that's not always the case. I mean, we looked at our reaction on Friday where it was never spontaneous. So what if we change one of these? Now delta H is positive, which means it's endothermic. Delta S is negative, which means negative T times negative delta S is also positive. So the whole entropy part of this function is now positive, and enthalpy is positive, which means that delta G is always positive, which means that it's non-spontaneous at all temperatures. And again, we're going to add more equations to this and more ways that we can use this. So try to keep the big picture in mind in that, why does this make sense? If I'm removing heat from the surroundings, that's decreasing the entropy of the surroundings. So that's a negative entropy. And my reaction itself goes from 3 moles of gas to 2 moles of gas, which is a decrease in entropy. So we're always decreasing the entropy of our system, and we're decreasing the entropy of the surroundings by doing this reaction. So it's always non-spontaneous. At least so far as we've talked about now. So really for these case 1, case 2, there's no reason to even really look at temperature, because if I change temperature, I just make it more non-spontaneous or more spontaneous, which doesn't really mean anything. It's either spontaneous or it's not. So if we look at a case where now delta H is negative and delta S is negative, this is where things are more interesting, because now I'm increasing, or I'm releasing heat. It's exothermic, negative delta H. So I'm releasing heat into the surroundings, which increases the entropy of the surroundings. But the reaction itself, or physical change here, process, is going from a liquid to a solid, which decreases entropy. It's like, this is the example that we talked about, is like, well, why is this spontaneous at different temperatures? And it's spontaneous at different temperatures because the amount of heat that gets released into the surroundings can sometimes be a greater increase in entropy than going from a liquid to a solid is a decrease in entropy. Because if delta H is negative and delta S is negative, then this overall will be positive. And so now I have a negative plus some positive value. And if I can make that positive value large enough by increasing temperature, or by increasing temperature in this case, then delta G will be positive, and the reaction will be non-spontaneous. If I decrease the temperature, then the negative T delta S gets smaller and smaller and smaller, since that's my positive value here. That means at some point it'll be less than delta H, and delta G will be negative. So it's going to be spontaneous when the temperature is low, and non-spontaneous when the temperature is high. So what's the last case then? Both positive. If both of these are positive, then it's the opposite of this. So case 3 and case 4 are the ones where we're balancing high temperature, low temperature, because I have these two values that are competing and can cancel each other out. Like, we can have the situation where delta G is 0. So if delta H is positive and delta S is positive, then this whole thing stays negative. And so increasing temperature will make this spontaneous, because the T is in that portion with the delta S. So as T gets larger, then this reaction will be spontaneous at some point. And as T gets smaller, then it'll be non-spontaneous at some point. Cool. And you can put this all into a nice little chart, which you could memorize the chart, but I think it's more important to think about it in terms of a bigger picture, in like, why is this spontaneous at all temperatures, non-spontaneous at all temperatures? And even with something like this, it's just a matter of plugging in some numbers. Namely positive or negative ones, because that makes things easy. Just as an example, if I take this equation and I say, okay, delta G equals, let's see, positive 1. Actually, positive 10 might be better. Minus t times a positive 10. What value of t would make delta G negative? Anything larger than 1? So larger values of t. If I use a smaller value of t, then this becomes positive. So if I put a 2, then this is 20. So 10 minus 20, oops, delta G. Right, so that's going to equal negative 10. So that's spontaneous. But if I put in 0.5 for t times a positive 10, then 10 minus 5 is positive 5. Right, so plug in numbers, see if delta G is negative. And actually, let's talk about this. I think it makes sense that delta G being negative is spontaneous. Because it's like mechanical potential energy, if my mechanical potential energy changes in a way that's negative, so it goes from higher to lower, right? Overall, that's a decrease in potential energy. That's negative. It's the same thing with chemical potential energy. So when delta G is negative, what we're saying is there's a change in potential energy that goes from higher to lower, which is spontaneous. If it goes from lower to higher, that means we're sort of adding this free energy in, which is non-spontaneous. Okay. So with this, now we can do some calculations and we can figure out what delta G is for different reactions. And we can now ignore the surroundings, really. In a mathematical sense, we can ignore the surroundings. We're taking it into account with delta H, but we don't really need to know anything about the surroundings to do the calculation. The big thing to pay attention to here is, or to pay attention to, is the units. So this is minus T, which is 25 degrees C, which is 298 Kelvin. Times negative, and this would be delta S. Delta S is in joules, but my delta H is in kilojoules. So I need to convert delta S into joules, or from joules to kilojoules. So this is 0.1205. And to be clear, it doesn't matter if it's joules or kilojoules. Really, most of the time, what we want to know is the sign. Later, it might matter. Actually, later it will matter more which one we use, but just be aware. Whoops. So delta G is equal to negative 101.591. Now, is this number going to get more negative or more positive as temperature increases? Yeah, I guess really what I should have done is like, that's what it would be at 25 degrees C. I mean, this is going to stay negative 137.5. But now I've got a negative times a negative, so it's going to be plus 35.909. And so if I increase the temperature, that positive number gets larger. So as temperature increases, delta G gets more positive. And we could calculate, well, what temperature does this then? Because right now we've got a negative delta G overall, but there's a temperature at which it'll stop being spontaneous. So we would need to find the temperature where delta G switches from being negative to being positive. So set delta G to 0, right? That would be the tipping point. If delta G is 0, so I set delta G to 0, then that equals negative 137.5 minus, and now we would want to find T times a negative 0.1205. And then we can solve that for T. And then any temperature larger than that would make this non-spontaneous. And now I do want to know what that is. It's 1,141 Kelvin. It's very hot. Oh, and I do want to ask a follow-up. Why would this reaction become non-spontaneous at a high temperature? No, not activation energy. It's exothermic, which a lot of most exothermic reactions are spontaneous. But look at the, wait, actually, they're both negative. This does become non-spontaneous. It becomes non-spontaneous at high temperatures. I would expect there to be a decrease in entropy. So I was thinking the chemical equation itself. Oh, well, oh, we know delta S is negative. Right. Okay, so actually, this hints at another thing that we have to look at. So we can't always just look at the things that are in the chemical formula to figure out how much the entropy is going to increase. All right, this looks like this is 1 mole of gas. It goes to 2 moles of gas. That's an increase in entropy. Delta S, though, is negative, which means that for this reaction, there's actually a decrease in entropy, which, well, we'll talk about other things that are related to delta S. So like just increasing the number of moles of gas is not everything. If I don't give you any other information and I just say like, is the entropy of this reaction positive or negative, and that's all you had to go on, this is an increase in entropy. If you have nothing else to go on. Oh, I'm reading it backwards, huh? I'm so sorry. I should have looked at it on here. I'm looking at it from over there, like from side on. No, this goes from 2 to 1. This totally makes sense. It's a decrease in entropy. Okay. Sorry. Yeah, it's going from 2 moles of gas to 1 mole of gas. There are things that could make it so that's not the case, but we are going from 2 moles of gas to 1 mole of gas. So that does decrease entropy, which means that the heat released has to increase the entropy of the surroundings more than the entropy of the reaction decreases. Which is why this is going to be non-spontaneous at some really high temperature. how did I see that as a plus? And all right, so let's just given delta H and delta S. We have something called standard states. Actually, this was in Chem 1. Calculated entropy or enthalpy, like the heat of things from standard enthalpies. But we had that same concept for entropy as well, and for Gibbs free energy. So where everything's in their standard states, you should remember our standard states as gas is at exactly 1 atm, liquid or solid, which is the pure substance in its most stable form, at 1 atm and a temperature of interest, which we're going to use 25 degrees C for just about everything. And then for things in solution, a concentration of 1 molar. And that works for enthalpy. For entropy, though, we kind of have to have another definition for what zero entropy is, or what we're basing all of our entropies on. But like enthalpy, entropy is a state function, so it only depends on the state. So what is my current state? What is my new state? The difference between those tells you how much the entropy changes. So entropy of the products minus entropy of the reactants gives us the change in entropy for that reaction. And so conveniently, from just even extrapolating down, like what if temperature decreases so much that the volume of something decreases to 0? That's a perfect crystal at absolute 0. And as a perfect crystal at absolute 0, where the atoms or molecules of the crystal are not moving, there is a single microstate. And so then according to Boltzmann's definition, the natural log of that one microstate would be 0. And so the entropy of that system would be 0. And that's a hypothetical perfect crystal because nobody's ever done it yet. Because you got to create a lot of entropy elsewhere to create 0 entropy in one spot. So all this really lets us do is base our entropies on that and then come up with tables of standard values at 25 degrees C or 298 Kelvin. And we're also adding in not just joules per Kelvin, but joules per mole Kelvin, because it's an extensive property. More stuff is also more entropy. So it depends on the extent or how much of it you have. Do want to point out, and we're going to look at like different things about entropy, but entropies, especially the state of matter, matters. Which makes perfect sense if you tie it back to the fact that, like, yeah, we talked about water going from a liquid to a gas increases entropy, and the values on the table reflect that. It goes from 70 up to 188. That's an increase in entropy. It's not the only thing that matters. There are other things that can be kind of tricky. And these were the kind of things that I was alluding to, but so state of substance, that's the one that we've seen, but also molar mass, particular allotrope, molecular complexity, and extent of dissolution. So we're going to go over those kind of quickly, but they all depend on this idea of how many microstates can I have. So the same reason that a gas has more entropy than a liquid applies to all of these concepts. And some of them more intuitive than others. So we already saw this one. Gases have more entropy than liquids, have more entropy than solids. That makes sense. They spread out, they've got more modes of energy. Another one is molar mass, which even the book says is too complicated to go into here, but things that are more massive have more places to put their energy. The differences in their different energy states get closer together as they get larger. So things that are have more molar mass generally have more entropy. And this is one that you just kind of have to know that these exist, although they are listed. Like if I give you a table of values and I want you to use graphite, the table that I give you will have graphite. and it'll have diamond. But to reason through why these have different entropies, standard entropies, you have to kind of know about the substance itself. I mean, we know that diamonds are very stable, they're very strong, they're very hard, and that's because all of the carbon atoms are locked into a crystalline pattern. So if you think of it as being a crystal, there are fewer energy states than in something like graphene or graphite, where it is sheets of carbon that can move around each other. So there's more freedom of motion in graphite than there is in a diamond. There are other things that have allotropes. If they are relevant, they'll be listed as different allotropes in tables where you look up these values. So it is something to keep an eye out for. Molecular complexity, and when I was reading that plus as an arrow and not the plus that it was, this is what I was thinking might be the reason. If I have, for a given state of matter, the entropy generally increases as it gets more complex. So almost literally, the more ways that it has to wiggle, the more microstates it has. So the more atoms that you have connected together for that individual molecule can have more ways to vibrate. And so all of those little linkages can, well, they can bend, they can actually bend, they can stretch, they can wag, which is different than bending sometimes. And then they could do so relative to each other, which adds microstates. So like in water, where you've got the two hydrogens, they can either do this, or they could do this, or they could do this. There's a lot of different ways for them to move versus just even like nitrogen monoxide. So generally, molecular complexity adds more entropy than molar mass. So like here, argon is more massive, but nitrogen monoxide has more entropy, or its standard entropy is higher. Another example of that, so carbon monoxide and ethene, C2H4, nearly the same molar mass, very, very nearly, but C2H4 has more molar entropy because there's more bonds between it's like carbon, carbon, there's a double bond there. All of those bonds can stretch and move and wiggle, and so that adds to the entropy of the molecule. And then the last one before you go, dissolution. So again, thinking about how do we add more microstates? If I dissolve something and it spreads out into a solution, then that is going to have more entropy because it's got more places to be in a solution versus a solid or a liquid. All right. Remember, there's no school tomorrow, which is random, but nice.